Hi students, hope everyone is fine and safe. It gives me immense pleasure to welcome you all to my new video, and today's video is about another interesting concept in the subject analog and digital communication. We're going to see noise in SSB-SC system. In this video, we're going to see the noise performance in SSB-SC system, and we're going to calculate the SNR and figure of merit for SSB-SC system. Before going to this video, I would recommend you people to go and watch the previous video where we have discussed about noise performance in DSB-SC system, right? This is going to be the same derivation, only a small modification will be there. So if you can go through the previous video, it will be very helpful for you to understand the SSB-SC system, right? So noise in FM system, noise in AM system, we already explained in detail about this in previous video, right? So we already know that we're going to transmit any particular message signal from a transmitter to the receiver. The noise will get added to that particular noise, right? And that noise is called as additive noise. As I said, whenever you're going to transmit any particular signal from transmitter, right, and through the channel, and the noise will get added to it, and the receiver, before reaching the receiver, right, the receiver will receive this particular signal M of t and as well as N of t, along with this N of t, right? That is, noise will get added to this particular receiver, and the receiver now have to overcome this particular noise, right, and it has to detect this particular original message signal, right? And that can be done by using some band pass filters and detectors. And you can see the receiving side, you have a band pass filter where it will band limit the signal. Here it is going to be an SSB-SC signal, right? So it will allow only the SSB-SC frequency band, and there itself some sort of noise will be band limited and will become a narrow band noise, right? And then it is sent to the detector, where detector will detect the original message signal from that particular signal, right? And I already explained about figure of merit, how to calculate figure of merit, right? So in order to calculate the figure of merit, we need to calculate the signal to noise ratio at the output side and signal to noise ratio at the input side, right? And we will see that. And before that, these are the very important calculations that you have to remember to calculate figure of merit, right? As I said before, the noise will get added to the original message signal, and that will be called as additive noise, right? And this noise is considered as a white noise or a Gaussian noise. That is because it will have an uniform spectrum over the entire band, right? So that will be eta by 2, right? The power spectral density will be eta by 2. So we can calculate the noise power based upon the multiplication of noise spectral density and as well as bandwidth, right? And similarly, the band pass filter, we know that the band pass filter we use at the receiving side before the detector, it will remove the unwanted signals. That is, it will band limit the signal and it will allow only the SSB-SC signal, right? And before the detector, the power spectral density can be mentioned as SNI is equal to eta divided by 2, right? So the total input noise power, this is common. The total input noise power can be represented as eta divided by 2 into 2 FM, right? Whereas here, it can be represented as eta into F. And now we consider this AM system as an SSB-SC system. It's the same explanation I'm going to give you, right? That is the original message signal where that is transmitted at the transmitting side. Like you'll add the carrier signal, right? And then you'll transmit it. That can be represented as f of t cos omega ct. And during transmission, what will happen? The noise will get added, right? And the receiving side, it will receive the original signal along with the noise, right? And then that is band limited, right? And it is sent to the detector. The detector here, as I said before, like in DSB-SC system, this is also called as coherent detection. It is called as coherent detection, right? That's because we're going to regenerate the same carrier which is used at the transmitting side. So if you're going to use the same carrier, which is used on the transmitting side, then that receiver is called as coherent receiver, or we can call it as coherent detection, right? That is the detection, the demodulation that happens with the knowledge of carrier, then that is called as coherent detection. If it happens without the knowledge of carrier, then that is called as non-coherent detection, right? And now this detector, this signal after product modulator, that is, you are multiplying the carrier signal along with this particular signal, and then it is sent to the low pass filter where it will allow only the low frequency components and will remove all the high frequency components. Correct? Right. And from that, we can able to obtain the original message signal, the original SSB-SC signal, right? And this is going to be the same derivation, only a small difference here, right? So as I said, we are going to first calculate noise power. Noise power, we know that N of T is written as NC of T cos omega Ct minus NS of T sin omega Ct, where this is in phase component and this is quadrature component. And this is the complete power, complete signal, but we are taking only the noise power because we're going to calculate the noise power, right? We consider the noise signal. N of T is nothing but, we can see here this N of T is multiplied with the cos omega Ct, correct? So N of T cos omega Ct. So if you multiply this cos omega Ct, we will obtain this particular expression cos square omega Ct sin omega Ct cos omega Ct. And I already explained this in previous video, right? We will, instead of this cos omega Ct, we can get this trigonometric value. And instead of this, we can write it this sin omega Ct, right? So this is the total equation which we obtained, right? The total signal. And this is the signal which is sent to the low pass filter where it will remove all the high frequency component. So this signal will be removed and this signal will be removed. Only the low frequency component will be allowed. So now you can see here the output noise power will be half of the input noise power. N of T is equal to 1 by 2 NC of T. This is same like DSB-SC, right? And only difference is here where we know we have already calculated the input noise power. Input noise power is eta into FM, right? And here we already know the how we will obtain the power spectral density, right? The power spectral density at the output of the synchronous detector can be obtained as output noise power spectral density is equal to 1 by 4 of input signal power density. That is, we know that power spectral density is average mean square value, right? We already know that the noise power is half of the, you can see here the noise power at the output noise power is half of the input noise power. So here the power spectral density will become 1 by 4 of the input noise power density, right? So, and we have already obtained this for DSB-SC system, it is just eta, right? This signal to noise power spectral density is just eta, whereas here for SSB-SC system, this eta divided by 2. This is the only difference. In DSB-SC system, we have double sideband. Here we have only single sideband. So it will be eta divided by 2. So what will happen here? So this will become eta divided by 8. So the total noise power can be calculated as eta divided by 8 into the total bandwidth, which is 2 FM, right? So we can write it as eta FM by 4, right? And from this, right, this is N0, and we can write this eta FM as Ni, correct? Ni, you can see this is Ni, right? So N0 is equal to Ni divided by 4. We can also rewrite it as N0 divided by Ni is equal to 1 by 4, equal to 1 by 4, correct? Right? And now we have calculated what is signal, what is noise power, right? And we have also calculated the ratio of noise power output to the input power, input noise power. Now we got to do the same thing for signal power. Signal power, we are going to use the same calculation. Only difference here is the signal power here, it will be same like the baseband signal because it is an SSB-SC signal. So it is f square of t, right? And to detect the signal power at the output, it will be the mean square value, which will be 1 by 4 f square of t, right? I have already explained this, right? So which means we can write it as 1 by 4 into SI, because this f square of t can be written as SI, right? So it will be 1 by 4 SI. So now S0 by Si is equal to 1 by 4. Now the gamma value you can calculate, that is figure of merit. We already know what is S0 divided by Si, and also we know that what is N0 divided by Ni, which is 1 by 4 divided by 1 by 4, that is equal to 1. It is same like the DSB-SC system, right? So you can see here the figure of merit is can be given as SNR output divided by SNR input, where we can rewrite it as S0 divided by Si by N0 divided by Ni by expanding this in this way, right? So that now we know S0 by Si is equal to 1 by 4 and N0 by Ni is equal to 1 by 4, where the figure of merit will be equal to 1. And you can see that the noise performance is very identical to the DSB-SC system, right? So if you understand DSB-SC system, you can able to derive SSB-SC system very easily, right? So today what we have seen is, we have seen the noise performance of SSB-SC system. I believe this video will be very useful for you. Thank you, my dear students.